Hello students, welcome to the next session. Today we'll be discussing about a very important topic, that is properties of determinants. So we start with the very first property, that is the value of the determinant remains unchanged when its rows and columns are interchanged. Now what does this mean? Remember, determinant is the value associated with a square matrix. So if I take a 3 by 3 square matrix, right? Let's say this is A11, A12, A13, this is A21, A31, this is A22. Let's say its determinant is represented by this particular symbol, right? If I interchange the rows and the columns, interchanging the rows and the columns mean the value of the determinant remains unchanged when its rows and columns are interchanged, means if I take out the transpose of this particular matrix and then I find out its determinant, its value remains the same, right? So if I say that determinant of this is, say, let's say of this matrix is equal to del, then on interchanging the rows and the columns, that is A11, this is A12, this is A13, A21, A22, A23, and then A31, A32, A33 will give us the same determinant value as del, right? Coming to the second one, that is, if any two rows or two columns are interchanged, then the determinant value changes. It becomes the negative of the previous one. What does this mean? If I have a matrix again, A11, A12, A13, A21, A22, A23, A31, A32 and A33. If I interchange any two rows, let's say I interchange R1 and R2. So on interchanging R1 and R2, R1 becomes A21, A22, A23, and this becomes A11, A12, A13, and this as it is. Then what will happen? If this determinant value was del, this determinant value will become negative of del, right? So these are the properties which we'll be utilizing in solving questions which are based upon properties. So we need to memorize these properties. The first one we have read is, when we interchange the rows and the columns, the determinant value remains unchanged. If we interchange two rows or two columns, then the value of the determinant becomes negative of the previous value. Third property, if any two rows or two columns are identical, then the value of the determinant is 0. Very important. If any two rows are identical, let's say we have 1, 1, 2, and this is also 1, 1, 2, and this is 5, 6, 7. Here R1 and R2 are exactly the same. So their determinant value would be equal to 0. Whenever you will calculate their determinant, it will come out to be 0. So two rows, either two rows or it can be two columns. If they are identical, then directly we can write that the determinant value is 0 in that case, right? Okay, another thing you need to remember before we start with property 4 is, if any of the rows has all the elements as 0, right? This is represented by determinant. I just represented the matrix. So if any particular, let's say R1 has all its elements as 0, then also the value of the determinant would be 0. So if any determinant is having elements 0 in any of its row or column, then the value of the determinant in that case also is equal to 0, right? Next we have come to property 4. If each element of a row or a column of a determinant is multiplied by a value k, then the value of the determinant gets multiplied with k. Now what does this mean? If we have a determinant, let's say this is A, B, C, D, E, F, G, H and I. If each element of a row, let's say if each element is multiplied, right, by k, our initial matrix was what? A, B, C, D, E, F and G, H, I. Now I have multiplied, remember, in case of determinants, unlike matrices. In matrices, we were multiplying each and every element with k. But here, we'll be going either row-wise or column-wise. So if we are applying an operation on a particular row, we'll be multiplying elements of that row only. Right? So scalar multiplication here does not mean that all elements are getting multiplied. Right? So we are dealing with the multiplication means we are multiplying either a row, elements of a row, or a particular column with a scalar multiplier. Right? So in this case, if earlier the determinant value was del, so now the determinant value becomes k times del. Is that clear? Next, property 5. If some or all elements of a row or a column of a determinant are expressed as sum of two or more terms. For example, if I have a matrix ABC, this is D, E, F, and this is X, Y, and Z. Right? And I apply the operation, that is R1 is R1 plus lambda R3. So this will become A plus lambda X, B plus lambda Y, and this will become C plus lambda Z. Dx, E, Y, all other elements will remain the same. Right? So how can we write this? We can write it as a sum of two determinants. That is, we can write this as A D X and this becomes B E Y and this becomes C F Z plus lambda X, this is lambda Y, this is lambda Z, right? This is D, E and F, this is X, Y and Z. So we have represented this addition that we have done, the representation of addition of two particular rows has been represented as the value of two different determinants. So it can be expressed this way. Okay. Now, our last property. If to each element of any row or column of a determinant, the equi-multiplies of corresponding elements of other row or column are added, then the value of determinant remains the same. It's just the extension of this particular property. Here also we have added rows, two rows, elements of two particular rows with a scalar multiplier. And here also they are talking about the same thing. If to each element of any row or column of a determinant, the equi-multiplies of corresponding elements of other row are added, then the value of determinant remains the same. So as you can see, the value of this determinant I can assume to be del plus lambda times, I take lambda as common. So what does this becomes? X, Y and Z, D, E and F, and this becomes X, Y and Z. And we have already studied this property that if elements of any two rows or two columns are same, the value of the determinant would be 0. So value of this determinant is del plus lambda times the value of this determinant is 0. So what is the value of the determinant? It is del. So it remains unchanged. This is what we are talking about. Right? It will be more clear once we start with the questions. So let us begin with exercise 4.2. The very first question, the instruction given is using the property of determinants and without expanding. In questions 1 to 5, prove that X, Y, Z, A, B, C, X plus A, Y plus B, Z plus C is equal to 0. This is what we are supposed to prove. Remember, in the second last property, what did we study? That the representation of, see, what is this particular thing? This is the representation of column 1 and column 2, X plus A. So I can simply express it as the sum of two separate determinants. So this is X, Y, Z and this is X, Y, Z, A, B and C. Remember, the elements of first two columns would remain the same, right? What will differ? We will represent them as the sum. So this is A, B and C, right? Now, we learned the property that elements of C1 and C3 are same. And in second determinant, elements of C2 and C3 are same. Therefore, their respective determinant value is equal to 0. So we can say determinant value of this is 0, this is 0. So the entire determinant value comes out to be 0. This is how we will be using the properties. I hope it's clear. Next, we do question number 2. So we have A minus B, B minus C, C minus A. This is B minus C, C minus A, and this is A minus B. And here we have C minus A minus B, B minus C. We have to put it equal to 0. Prove it equal to 0, right? What if I add R1 plus R2 plus R3? If I add all the three, remember if I add here minus B plus B gets cancelled, minus C plus C, and A and minus A gets cancelled. So I get a 0 over here. Likewise, here also all these elements will get cancelled. So a 0 here, likewise 0 here. This is B minus C, this is C minus A, this is C minus A minus B, this is A minus B, this is B minus C. Initially, when we were doing property 3, I told you if the elements of any row or any particular column are all 0, then the value of determinant is equal to 0. So elements of R1 are 0. Therefore, del is equal to 0. Determinant is equal to 0. Right? I hope it's clear. Move on to question number 3. This is 2, 3, 5, 7, 8, 9, 65, 75 and 86. We have to prove it equal to 0. Now, how can we prove it equal to 0? Let's say we have, let's say 2, 3, 5 be as it is, 7, 8 and 9 as it is. Then we can write 65 as 63 plus 2, 75 as 72 plus 3 and 86 as 81 plus 5. Right? Sorry, we have to prove it equal to 0. So as we already know that we using property 5, we can represent them individually as the sum of two determinants. So this can be written as 2, 3, 5, 7, 8, 9, 63, 72, 81 plus this can be written as 2, 3, 5, 7, 8 and 9 and 2, 3, 5. Right? Further, I can write this as, this is 7, 8, 9. This can be written as 9 into 7, right? 9 into 8, and this is 9 into 9. Now, if I take 9 common from C3, so what I have? I can take 9 as common from C3. 2, 3, 5, 7, 8, 9, 7, 8, 9 plus 2, 3, 5, 7, 8, 9, 2, 3, 5 as elements of C2 and C3, and in second determinant elements of C1 and C3 are same. Therefore, del 1 will be equal to 0 and del 2 will also be equal to 0, because we consider this as del 1 and let's say this comes out to be del 2. So 9 into 0 plus 0 equal to 0. So let's say del is equal to del 1 plus del 2. Right? So this is why we get it as 0. I hope it's clear. Please practice questions till here, students. In the next class, we'll begin with question number 4 onwards. Thank you.